let's do a couple more examples using the radius and interval of convergence. So here's another series. So we have the summation from n equals 1 to infinity of x minus 6 to the n divided by n to the power of n. Okay, so in this point, I think the root test is going to be a little easier to work with. So we're going to use a root test. Okay, so we need to figure out what the value of L is going to be. So remember that the root test says that the limit as n goes to infinity of the nth root of the absolute value of a sub n has to be less than 1. Okay, so here what we're going to do, let's go ahead and plug them into this thing. So limit as n goes to infinity, the nth root of the absolute value of x minus 6 to the power of n divided by n to the n. Okay, so let's change this nth root to a rational exponent. So we're going to have the absolute value of x minus 6 to the power of n over n to the n of 1 over n. So now we're going to distribute this 1 over n to both of these guys. So you're going to have the limit as n goes to infinity of absolute value of x minus 6. So the n's are going to cancel out. And on the bottom, this n is also going to cancel out. So you're left with n. Okay. So now we're going to have the limit as n goes to infinity. We can pull out the n because the n is always going to be positive. So you have 1 over n. And you're left with the absolute value of x minus 6 staying in the absolute value. So I can put this to the front because the limit is only wants the value of n. So you have the absolute value of x minus 6, the limit as n goes to infinity of 1 over n. This thing is just going to be 0. So when I multiply this absolute value times 0, what you're going to get is 0. Notice that 0 is always going to be less than 1. Okay, so this thing is always going to converge. So no matter what value of x I plug in there, it's always going to converge, because if I plug in x equals to 1,000, well, this limit is always going to go to 0. So that 1,000 is going to be just zeroed out when you multiply it by 0. So how do you write the radius of convergence if everything just cancels each other out? Well, since it always converges, let me just write always converges. We would say that the radius of convergence is equal to infinity, because they will converge for all of them. And the way that you write the interval of convergence is just from negative infinity to positive infinity. So imagine just writing it as regular interval notation, as all real numbers, right? That's how you would write the interval of convergence. Okay, so sometimes this does occur. Things will just cancel each other out, and you'll just get that. Okay, let's do another problem. So let's say we want to find the sum from n goes from 1 to infinity of x minus 3 to the power of n divided by n. Okay, so we want to find this, the radius of convergence and also the interval of convergence. So notice that this looks a lot like the first problem, except that we don't have a power of n on the bottom. Okay, so we can definitely still use the root test if you guys want to. So we can use the root test again. Okay, so let's use root test. You can also use the ratio test if you want to. So the root test, so we're going to take the limit as n goes to infinity of the nth root of the absolute value of a sub n. So you're going to have the limit as n goes to infinity of the absolute value of x minus 3 to the power of n divided by n. We're going to change this to a rational exponent, 1 over n. So now we're going to plug that thing in there, in the inside. So we have the limit as n goes to infinity of, the n's cancel out, so you're left with x minus 3 on the top. And on the bottom, you're left with n, 1 over n. Okay, so now you're going to have, we can pull out the absolute value, x minus 3, out. You're left with the limit as n goes to infinity The absolute value of this guy is not going to affect it, so you're just left with 1 over n to the 1 over n. And we said when we covered the root test that this thing is just going to go to 1. So all I'm left with is x minus 3. This whole thing is just 1. So you're going to be times 1. So you need this thing to be less than 1 in order for it to converge. Okay? So right off the bat, we already see that x minus 3 has to be less than 1. So our radius of convergence is going to be equal to 1. Okay? So now all we have to figure out is what is my interval of convergence. So let's solve this this absolute value inequality. So x minus 3 is less than 1. And then we're going to put a negative 1 over here. We're going to add 3 to all sides. So I'm left with x is between 2 and 4. Okay, now remember, this is not the interval of convergence. What we got to check now is when it equals 2 and then when it equals 4. So now we have to check the endpoints. We have to make sure that this checks. So now we're going to start off by plugging in 2 first. Okay, so we know that the sum from n goes from 1 to infinity of x minus 3 to the n over n. Okay, so what we got to do, let's plug in 2 first. Okay, so we're going to have the sum from n goes from 1 to infinity of 2 minus 3 to the n over n. Okay, this is going to give me the sum from n goes from 1 to infinity of negative 1 of the n over n. Okay, this is an alternating series, so we will use the alternating series test. Okay, and remember, the alternating series test says that b sub n is decreasing, and also it says that if you take the limit as n goes to infinity of b sub n, if it equals 0, if both of this satisfies, then this converges. Okay, so now we have to check this. So b sub n in this case is going to be equal to 1 over n, because that's what's next to the alternating series. Okay, now we've already done this problem. This is decreasing. Okay, this is a problem that we did in the alternating series test video. So we already know that this is decreasing. When we take the limit as n goes to infinity of 1 over n, we know that this is 0. So guess what? At x equals 2, this converges. So is 2 included? Yes, include 2 in the interval. So we are going to include this 2 in there. Okay, so 2, you are included. So when you go over here, you have to change this to an equal sign. Okay, now let's check, is 4 also going to be included? So now we're going to check out 4. Okay, so we're going to have the sum from n equals 1 to infinity of x minus 3 to the n divided by n. Let me plug in the 4. So the sum from n goes from 1 to infinity of 4 minus 3 to the n over n. This is equal to sum as n goes from 1 to infinity of 1 to the n over n. Well, 1 to the power of n is not an alternating series. There's no negative there. That's always going to be equal to 1. You're left with 1 over n. This thing is a harmonic series or a p series, right? So if you do p series, p is equal to 1, okay? And if since it equals to 1, all p series that are greater than 1 are going to converge. Since if they're less than or equal to 1, then they're going to diverge. So this diverges. So you can either do it by p series or harmonic series. Okay, so this is going to diverge. So at x equals 4, this diverges. So in that case, x equals 4 is not included. So we are not including x equals 4. Okay, that one stays the same. So my interval of convergence will be from 2, which we're including, all the way to 4. Okay, and remember our radius of convergence was equal to 1. Okay, which is in the previous one right here, r equals 1. Okay, so notice that you always want to check the endpoints because you never really know what's going to happen if it's going to converge or diverge. Okay, now let's do one last one. Okay, so let's say we have the sum from n goes from 0 to infinity of n factorial x to the power of n. Okay, so here I think it would make sense to use the ratio test. Okay, so let's go ahead and use the ratio test. So we need to figure out what a sub n is. A sub n is so it's going to be n factorial x to the n. And then a sub n plus 1 is going to be n plus 1 factorial x to the n plus 1. So now using the ratio test that we're going to use says that we're going to take the limit as n goes to infinity of the ratio of a sub n plus 1 divided by a sub n. So this is going to be the limit as n goes to infinity. A sub n plus 1 is going to be n plus 1. Whoops, that's wrong. N plus 1 factorial x sub n plus 1. And on the denominator is going to be n factorial x to the n. Okay, so we're going to have the limit as n goes to infinity. So the top part, we can rewrite it as n plus 1 times n factorial, or we can write everything out. Then x to the n, x to the first power. And on the bottom, n factorial, and then x to the n. So notice that the x to the n's are going to go away. The n factorials go away. And you're just left with the limit as n goes to infinity of the absolute value of n plus 1 times n. So I can or take this guy out, the absolute value of x, and just take the limit as n goes to infinity of n plus 1. Well, this guy right here is always going to go to infinity. Okay, so regardless of whatever x is, this thing is always going to be bigger than 1, which is kind of the opposite of what we did in the first problem. Okay, so this one, it doesn't matter what x is, this thing is always going to diverge, always diverges, because this limit here is always going to go to infinity. So what do we say? So the radius of convergence, whenever it's always diverges, is going to be 0. That means that there is no numbers that are going to make it converge. And also the interval, you would just say is 0. It's empty. Okay, it's an empty set. So you can write this, you can write something empty set. It just doesn't exist. Okay, so I gave you kind of an example of every single type of case. You always want to make sure that you check your endpoints. Sometimes it will matter, sometimes it won't. Sometimes you might have an interval of convergence. Sometimes you might not have an interval convergence. So it really just depends. It's just a little lengthy, but this is how you really want to be able to do it.